My name is Greg Reynolds. I'm an applications engineer at Cypress Semiconductor. This video is the second part of a brief introduction to the low power modes available in the PSOC3 family of devices. The first video in this series introduced the four power modes of the PSOC3. The power modes in order of typically decreasing power consumption are active mode, alternate active mode, sleep, and hibernate. For the purposes of this second video, it is assumed that you already viewed the first video and are familiar with these power modes. Also, it is assumed that you are familiar with the basics of using PSOC Creator. There are many documents and videos available at cypress.com to help you come up to speed on PSOC Creator if you need them. This video will demonstrate some simple example code running on Cypress's CY8C Kit 030 development platform, and will show all four power modes in action. The development board has been configured so that the meter will only measure the power consumption of the PSOC and not the surrounding peripherals, such as the LCD module. For clarity, this example project uses just a few components to demonstrate the various power modes. A real-time clock or RTC component simply keeps time after startup. The timer component generates a pulse every 250 milliseconds, which is visible to the user through the LED connected to pin 6.2. The character LCD component is used to output a visual description of what mode the device is currently in and to display the RTC time. Pin 6.1 is configured to have an internal pull-up and is connected to a momentary push button used to trigger pin interrupt events for use by the firmware. These components were chosen because they are built from elements that behave differently across the four power modes. They could be substituted with any number of different functions. One thing that is often overlooked when developing a low-power system using PSOC Creator is the built-in debugging capabilities of PSOC. Because real-time debug is available in the PSOC3 device, the debug interface can remain active even when the device is in a sleep state. This may result in higher power consumption than would be present in the final application. To eliminate this possibility, when debug is not needed, you can disable the debug logic. It doesn't consume a lot of power, but sometimes can be a distraction. Just be sure to enable it again if you need to run the debugger. For this example, the clocks are all being derived from the IMO, which is being run at 24 MHz. The project is not really doing anything that requires 24 MHz, but it helps demonstrate the differences in the power states. There are cases where running at higher clock speeds results in less power consumption, but that depends on exactly what the firmware is doing and is a topic for another time. This design also requires the use of a 32 kHz crystal for precision timing using the real-time clock component. One other thing to note is that the 1 kHz ILO is required for the PSOC to operate properly in sleep mode. If the ILO is not configured for 1 kHz operation by default, you may need to use the API in your initialization code to enable it. What you're seeing now is the code that will be running on the PSOC3 for this demonstration. This project is a simple loop which cycles through the four power modes discussed earlier. Line 20 disables hardware regulator buzzing. As of the creation of this video, there is an open errata item related to the use of hardware buzz and sleep modes. A software workaround was implemented in Creator version 1.1, and a silicon fix will also be released. In the meantime, hardware buzzing should be disabled as shown here. Please refer to the latest hardware and silicon documentation for the status of this issue at the time you're viewing this video. Line 21 sets pin 6.1 as a pin interrupt source with a falling edge trigger. Line 22 sets the 32 kHz crystal drive mode to low power during sleep. After initialization, the major components are started, shown in lines 27 to 29, and the code enters the main loop. This section of code demonstrates active mode operation. Until the button is pressed, the real-time clock is updated on the LCD while the timer runs in the background and flashes the LED. Once the button is pressed and the LCD is cleared, and the firmware moves on to alternate active mode. Let's watch it in action. The real-time clock and timer start counting very soon after reset is released, and you can see the time being updated on the LCD and the LED flashing. You can also see that this particular design draws about 8 milliamps of current in active mode because everything is up and running constantly. There are certainly ways to reduce power consumption in active mode, but that is a topic for a different video. This is the section of code that enables alternate active mode. The API accepts two arguments, a wake-up time and a wake-up source. The defined constants are bit masks and can be ORed together to allow for multiple wake-up sources. In this demo, we'll be setting the PSOC to wait from alternate active mode only when an interrupt triggers, which means that the real-time clock interrupt will return the device to active mode once every second. When the real-time clock interrupt occurs, the time is updated on the LCD. The timer will also continue to run in alternate active mode, meaning that the LED will continue to flash. Once the button is pressed, the firmware clears the PQ interrupt and moves on to sleep mode. Let's watch it in action. The real-time clock is still running from where the code was in active mode, so the time continues to update from where we left off. The timer has also been running, so the LED has continued to flash. You can see that current consumption dropped when the PSOC entered alternate active mode, but since most resources in the PSOC are still active, the current drops only so much. The power savings comes from the fact that anything which does not require the CPU can continue to run, and the CPU is only active for a very short time to update the LCD with the latest time data. This is the section of code that uses sleep mode. Just like with alternate active mode, the sleep mode API accepts two arguments, wake time and wake up source. And, just like the alternate active API, the defines can be ORed to allow for multiple wake up sources. In this example, we're setting the PSOC to wake upon a PQ interrupt, a button press, or the interrupt from the 1 pulse per second timer that the real-time clock uses. You will notice that entering sleep mode requires some additional steps that alternate active does not. This is because most resources in the PSOC are disabled during sleep, so you need to properly prepare for it. Most creator components have a sleep API which saves the current state and stops the component. If returning to the exact state that the component was in before sleep is not important, or if the component is not needed after sleep, then stopping the component will result in the same power savings. The timer must be put to sleep, shown in line 90, because its resources are disabled in sleep, but the real-time clock continues to run. The LCD requires no special attention in this case because it uses a separate controller. We simply set the pins to a high Z state, shown on line 92, to prevent any leakage. Once the components have been properly prepared for sleep, you should call CYPM save clocks, line 93. This function prepares all timing sources for sleep by saving the configuration and switching all timing for any resources that are active during sleep to use the 3 MHz IMO and the 1 kHz ILO. Upon wake-up, you should clear any pending interrupts by reading the PM status register, shown on line 98, and then restoring all timing to its previous state by using CYPM restore clocks, line 99. Once the clocks have been restored, any components that were put to sleep using their API can be awakened using the corresponding wake-up API. You should also restore any pins to their previous state. Let's watch it in action. When the PSOC enters sleep, you can see that current consumption dropped considerably. Most resources inside the PSOC are turned off, including the timer, so the power savings come from the fact that the great majority of resources are only active for a very short time, just long enough to update the time on the LCD. It's possible to operate in an average current of 1 microamp in sleep with the real-time clock running. Some components have the option to remain active during sleep and will continue to draw current, and any GPIO pins will remain in the state that they were in when the PSOC entered sleep, so be careful to ensure that no unintended current sources or sinks are present. This is the section of code that uses hibernate mode. Hibernate is the lowest power mode that the PSOC3 has, and all but the most critical system resources are turned off. The API accepts no arguments because the only wake-up source available in Hibernate is a PQ interrupt. Since almost everything shuts down in Hibernate, we need to put all components to sleep using their API, just as we did for sleep mode, and shown here on lines 127 to 130, and then call CYPM Hibernate on line 131. Once a PQ interrupt has triggered a wake-up, we follow the same wake-up flow as with sleep mode: restore clocks, restore pin drive modes, wake components, and clear interrupts. Let's watch it in action. The real-time clock has been running this whole time in active, alternate active, and sleep modes, but not in Hibernate. If designed properly, a system with a PSOC3 can draw as little as 200 nanoamps in Hibernate. Only the most critical resources are active inside the PSOC right now, and nothing will happen until a PQ interrupt or a reset occurs. When the button is pressed and a wake-up occurs, the PSOC3 returns to active mode and our firmware loops to the top again. Note that the real-time clock was turned off in Hibernate, so the displayed time hasn't changed much from when it was last displayed on the LCD. As you can see, it is easy to switch between power modes within a single PSOC 3 firmware project. The APIs used in this video are described in detail in the Power Management section of the PSOC Creator System Reference Guide, available under Help, Documentation in PSOC Creator, which you can download today for free from the Cypress.com website. Additionally, there are application notes and code examples available at Cypress.com to help you quickly learn how to use the various power modes available in PSOC 3.